going to do a quick explanation of the thing I forgot to mention in my previous video, which is why, where's the geometric series, distribution, I mean, not series, sorry. So the geometric distribution, why the mean or expected value is 1 over the probability. So if you think about it intuitively, it makes sense. So if I give you a coin, 50% chance it lands on head, 50% chance it lands on tails, the expected value would be 2, which seems obviously that makes sense intuitively. Even the same with the dice being at 6 for each of the faces of the dice. But I will show you a bit more, well, something that makes sense to me, something I came up with. I mean, obviously, definitely it's not original, is it? But it's just what makes sense to me, and you can then use the same sort of similar strategy to find the variance as well. So, we're stopping. The idea of this is you stop after you get a success, and so if I were to write the chance of it being 1, only doing it 1 time is p, because you have to succeed on the first time. To get 2 is failing on the first time and then succeeding on the second time. 3 is failing on the first 2 times and then succeeding on the third time. And so you see they've all got this p, and then it's 1 minus p to the n minus 1, which is like this nth term. Yeah, because you're failing n minus 1 times and then succeeding once in that order, because you can't just succeed sometime and fail immediately after, because it immediately stops as you succeed. Anyway, so now to find the expected value, we've got to times each of this 2, this 3, this n, and so on for all of these n's with the probability of getting n. So that becomes the expected value of x in this, it doesn't matter, is equal to p, because 1 times p is p, and then 2p 1 minus p, and then 3p 1. Okay, that was bugged out. Okay, 1 minus p squared, and so on. So first we can take out a factor of p. So rewrite it as 1, 2, lots of 1 minus p, and then 3, 1 minus p squared plus ... And I suppose the thing to realise now is that we've got essentially an infinite series. So this term inside the bracket is just 1 minus p, plus 1 minus p squared, plus ... for after infinity, and then 1 minus p, because there's 2 of them and there's only 1 of them, plus 1 minus p squared, and I mean we can just plus ... and we can just keep going down for however many there are. So there's 3 of those, and then for the next one there'll be 4, so be pile of 1, pile of 2, then a stack of 3, then a stack of 4, and so on. But you get these infinite series, and obviously this one, if you don't know the infinite sum of infinite geometric, I mean this is not making any sense, but it's just 1 over 1 minus p, because that is the time we're timesing by 1 minus p each time, and so that's the sum of that is going to be equal to this, and that's just equal to 1 over p, and then that's just 1 over 1 minus p times that, and the next one's 1 minus p squared times that, and so on. So this new sequence, so the sum of all of this is just going to be p 1 over p plus 1 minus p over p plus 1 minus p squared over p plus ... And then from this, these p's cancel out, and because they cancel out. So we then get 1 plus 1 minus p plus 1 minus p squared, which is the same as this one, which we already know is equal to 1 over p. So the entire sum is 1 over p. Alright, so that's what the expected value is, and that's why the expected value is that, just a bit more rigorously, I suppose. And you can do a similar thing for the variance. So the variance is the sum of the square values. It's like the sum of the probability times the square minus the mean squared. I mean, oh, it's what the mean in the squares minus the square of the means, isn't it? Yeah. So we get, I could write it like that, mean that x squared minus x squared. So that's the variance, and you can do a similar sort of thing here. So we already know this is, I would suggest if you want to have a go at doing the same thing for the thing, you pause the video now, but just quickly I'll go through it as well, but just going through it now. So we already know that's 1 over p squared, so it's just going to be the mean of the square values of x, where, or this, I'm just, for the whole time I've been assuming x is just this distribution here, so it's just being distributed like that. So now we'll just worry about this sum. So instead of getting 1 plus 1, 2p, 1 minus p, and so on, we now get p times, I'm just going to take the factor out immediately because we already went through this. So 4, lots of 1 minus p, and then plus 9, lots of 1 minus p squared, and so on. And the thing to realize here is now this is just the difference between this and this is 3, that one difference between that one's 5, so we can do a similar sort of thing now. So it's 1 minus p squared, plus this time now 3 1 minus p plus 3 1 minus p squared, plus dot 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 and plus dot 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 again, and now it's 5 and 5 1 minus p squared, and the same thing goes because the difference between two consecutive squares, so x plus 1 squared minus x squared, which is essentially what we're doing, because the difference between that one's 4, that one's 9, the next one's going to be 4 squared, and so on. The difference between that two is going to be equal to 2x plus 1, which is just the odd numbers. So we essentially get this stack of odd numbers. So for the nth one, it will be 1 minus p squared plus 3 1 minus p squared plus 5 and 1 minus p, 1 minus p to the n minus 1, 3 1 minus p to the n minus 1, 5 1 minus p, and 7, and so on. And now we can just find the sum of these. So that one will be, we already know that's 1 over p, and that one's going to be 3 plus 3 1 minus p over p, and that's 5 1 minus p squared over p, and 7, and so on like that. And we all know these p's cancel out because the p before, so we can, the whole thing, this whole sum is equal to 1 plus 3 1 minus p plus 5 1 minus p squared plus 7 1 minus p cubed, and so on. And if I was to, well, I mean, you can do the same thing again, right? So you get 1 plus 1 minus p, I'm just going to speed through this, plus dot dot dot, and that's, we already know that's equal to 1 over p. The next one is going to be 2, the next one's also going to be 2, so we now get 2 1 minus p over p plus 2 1 minus p squared over p, and that one's also going to be 2 because the difference between these ones is 2, in the same way that the difference between them was 1 3 5, and just the odd numbers, the difference between these are always going to be 2. So we get this sum now, so I can take out a factor of 1p, and then that is I can also write that as 2 plus 2, 1 minus p. And if I just take out this minus 1 over p plus, because if I add 1 over p and then subtract 1 over p, so they're all 2, because this one's a 1, so it just makes it nicer, I suppose. And then that's 2, 1 minus p squared, plus dot dot dot. That sums to 2 over p, and we're timesing it by 1 over p, so that's 2 over p squared. And then we're subtracting 1 over p, so we get 1 minus p, yeah, that's fine. And then, so that's that sum of this, going back to this, that's the sum of that one. That then sums to 2, because 2 minus 1 is 1, so that's 1 over p squared minus 1 over p, and we can rewrite 1 over p as p over p squared, so that's 1 over minus p over p squared, which is our variance equals var x. And that's just, well, obviously there's, I don't know, this is the way I did it and how I came up to find the variance and the mean, but I'm sure that there's probably a better way of doing this. But that's just, I felt I should probably explain, and then just using this similar sort of method I've done over here to like do it. If you do it a couple of times, you can then find the variance of x as well. So yeah, that's, well, my proof of why the expected value of x for a geometric sequence is 1 over p and the variance is 1 minus p over p squared. Goodbye.